Okay, thank you. So, yes, the title of my talk is Logarithmic Units and the Continuous Wavelet Transform. And in some ways, this is going to be a fairly unusual talk because I'm going to be defending the case for allowing logarithms of non-dimensionless quantities, such as frequencies, without first requiring non-dimensionalization. I'm going to explain how this can be done in a mathematically consistent manner, and I'm going to defend that it's useful. So this idea is not new, but when it's been proposed in the past, it's generally not been received very well, I think, and it certainly doesn't seem to have been adopted as standard practice in the scientific community. And so I think part of what's going to be new in my talk is defending the strength of the case for this. So I want to start with a preliminary observation that will seem a bit random and perhaps even a bit technical or boring, but it will definitely be relevant or useful. So given function g and positive constants a, b, and c, I want to consider the following three expressions. The first is just the integral from a to b of g of x over x. And the second, we change the logarithms in the bounds of the integral, and we have e to the zeta d zeta. And the third is now where the c enters. We have a over c and b over c in the limits rather than just a and b, and we've got c again here. Now, those of you who are very astute with calculus may have recognized already these three expressions are all exactly equal to each other. So you can get from expression 1 to 2 by zeta equals log of x, and from 1 to 3 by psi equals log x over c. But if I were to ask you, so I said that these now, they are the same value, so the three different expressions for the same value. If I were to ask you to rank these three expressions from most simplified form to least simplified form, how would you do that? Would anyone like to offer a ranking of these three expressions from what you would consider to be most simplified to least simplified? Yeah.
Exponentials are actually the 3 to 1 is what, and from the engineering, because we like exponentials.
Yeah.
But I agree, you would go 1 to 3 in general, I would say.
Okay, so your suggestion was 3, 2, 1. Yeah.
Expansion and
yes. Yeah. So but you're saying that 3 and so you consider 3 to be more simplified than 2, or 2 to be more simplified than 3?
Similar, but more simplified than 1 for sure.
Okay, interesting. Thank you. Yes, thank you. Anyone else? Oh. Okay. Okay. Yeah. So basically, what I was kind of anticipating is that people would consider 3 to be the most unsimplified. Expression 3 is the most complicated, whereas 1 and 2 is where it seems to be a bit more of a tricky question. Which one would you consider more simplified? Thing is, so 1 and 2 I would regard as different physical perspectives on the same mathematical object. And often having multiple perspectives is useful. But this 3, it's like 2, but with a redundant variable c. So in other words, the only difference between 2 and 3 is I've got this c in the denominators here and this x and the c here. So c is redundant, right? Because it's the same as these expressions without the c. Okay, so we'll return to this later on. So I want to talk about quantities with dimensions or with units. So we have a system of numbers for quantifying things. So for example, we can say there are 5 objects in the cupboard, or dividing this out equally, we each get half of an apple. Now I want to consider the following conversation. Person A, well done for doing the marathon yesterday. I hear you were quite fast. How long did it take you? Person B, I did it in 26.4. So yeah, not too bad. Person A, sorry, how long? Person B, 26.4. So still room for improvement. I'm nowhere near as fast as person C, who did it in 13.2. So person A says, okay, so you did it in the same time it would have taken person C to do it twice. In other words, the time it took you to do it is 2 times the time it took person C to do it. But I still don't know how long it took you or person C to do it. So what do we conclude from this conversation? To quantify time durations, you can't do it using just a number like 26.4. You use the combination of a number and a multiplicative unit. Multiplicative because person A still knew that from the fact that 13.2 is half of 26.4, person A still knew that person C took half the time that person B did, even though person A didn't know how long each of them took. So, for example, possible unit of time would be egg boilings, how long it takes to boil an egg. So 26.4 egg boilings means the same as 26.4 times an egg boiling, which is the same as 2 times 13.2 egg boilings. And there are various other ways that we could express this same quantity. It's a number multiplied by a multiplicative unit. And there are many other physical entities that are similarly quantified in terms of the combination of a number and a multiplicative unit. A number without a unit is called dimensionless. So, for example, just the number 5 is dimensionless. But we need to be aware there are also dimensionless units. So, for example, a radian is actually just the dimensionless number 1. A percent is actually just the dimensionless number 1 over 100. And I say that 2 quantities are of the same dimension if they can be measured with the same unit. So, for example, 2 lengths are of the same dimension, 2 masses are of the same dimension. Okay, so far we've considered expressions of the form dimensionless number times a dimensioned quantity. Now I'm interested in talking about multiplying dimensioned quantities together. So recall that 2 non-zero valued variables are said to be in direct proportion with each other, so x and y, if multiplying one of the variables by a given factor multiplies the other variable by exactly the same factor. Okay? So a way we can represent this is by this equation. So the ratio of y values matches the ratio of x values. And the common notation for this is just y is proportional to x. And note that this definition is applicable even if x and y are not dimensionless numbers. So, for example, y could be a length and x could be a time, and they can and this definition that I've got here, the ratio of the y's equals the ratio of the x's, is still applicable. Now, so this was for 2 variables. Sometimes the relationship between 3 variables takes the form of a kind of bivariate direct proportionality. So I'll give an example to explain. A rectangle's area, how that's related to its 2 side lengths. For any 2 rectangles, the ratio of the areas is equal to the ratio of the shorter side length times the ratio of the longer side lengths. Okay. But this is true, but this is a very cumbersome way of expressing the idea. Now, if I have dimensionless numbers, z, x, and y, with this kind of relationship, in other words, ratio of z values equals ratio of x values times ratio of y values, then this type of relationship can be expressed much more simply as follows, that z is proportional to the product of x and y. So this proportionality, this is still proportionality between 2 variables, but this relationship can be simplified as just that the variable z is proportional to the product of x and y. And so that's what happens in the case where we're dealing with dimensionless variables. But here we've got lengths, which are not dimensionless. And so the idea is, so the same simplification, right? So this is a simplified version of this. The same simplification can be achieved for dimensioned quantities, such as lengths, by allowing multiplication of dimensioned quantities. In other words, we would just say the area of a rectangle is proportional to the product of its shorter side length and its longer side length. And if there isn't an already existing equation for areas prior to formulating this principle, then we can simply define this proportionality to be an equality. In other words, we say the area of a rectangle is equal to the shorter side length times the longer side length. And so this equation 4, you notice that's much simpler than what we had in our original expression. So here's our original expression. But we can, by allowing multiplication of dimensioned quantities, we can express it much more simply like this. And so this is where we get expressions like centimeters squared or feet squared from. So I know I'm talking about things that are very basic that you did in sort of primary school, but it's actually good to really think about the details of what's going on, how and why does this work, and this is what's really going on. And the thing I want to emphasize, there's no such thing, so I've talked about feet squared, there's no such thing as a foot multiples of a foot. There's physically no such thing. In the way that there could be 3 multiples of a foot, that makes sense, but there's no such thing as a foot multiples of a foot. And so the idea of something like feet squared is just a mathematical tool. This multiplication of dimensioned quantities like length is just a mathematical tool. And while square feet is quite an intuitive unit of area, other derived units, in other words, units formed from multiplying other units together, have a much less immediately intuitive meaning for the quantity they seek to quantify. For example, energy is measured in kilograms meters per second squared. But the physical meaning of a kilogram meter per second squared is not immediately intuitive. So I've talked about multiplying dimensioned quantities together. We can also raise dimensioned quantities to non-integer powers. So for example, for Brownian motion, the drift coefficients, that's kind of the speed at which the Brownian motion sort of tends to go in some direction, is measured in meters per second, what you usually expect for speed. But the diffusion coefficients, which would measure the rate at which your sort of uncertainty of where you are grows, this would be measured in meters per square root second. Now, again, the physical meaning of that is not necessarily immediately intuitive, but that's how you'd measure it. And then another example is that the fracture toughness of a material is typically measured in megapascals times square root meters. Okay, so I talked about how we can multiply dimensioned quantities and raise them to powers. Now, in the international system of quantities, there are 7 different fundamental dimensions, for example, mass, length, time, and then there are 4 others, from which other dimensions, such as length squared, which we use to measure areas, can be derived from multiplication and raising to powers. And so what this then means is that in the international system of quantities, the set of all positive valued quantities, including the dimensionless ones and the non-dimensionless ones, can be represented as a space of 8-dimensional vectors. So that's this set V. So we first have the dimensionless number before the unit. So I just consider positive ones, and that can be expressed as e to the power of a real number. And then for each of the fundamental units, I have a number that I can raise it to the power of. And so that gives me 8 degrees of freedom for describing the set of all positive valued quantities. So I can think of these as 8-dimensional vectors. And then what happens mathematically is that the vector addition operation, adding vectors, that becomes multiplication of physical quantities. And the sort of multiplying a vector by a scalar number operation, that translates into raising one of these quantities to a given scalar power. And so, don't worry if you didn't follow all of the details exactly, but the key point is we're already seeing a kind of a logarithmic relationship. The addition is the addition operation is multiplication, and the multiplication operation is raising to powers, which is kind of how the motivation behind logarithmic scales. Now, why do we not see expressions like cos of 3 meters or log of 50 hertz or half to the power of 10 minutes? So I think that the real reason why we don't see expressions like this in science is because of the Buckingham Pi theorem. And so this is based on the vector space structure that I described. And I won't give a precise statement, but the sort of intuitive or informal statement of this theorem. If I want to express the relationship between a set of physical variables which may have units, and if this relationship requires the use of some operation G besides just multiplication and raising to powers, so for example, things like cos or log or exponentiation, these are examples of possible operations G, then the theorem tells us this relationship that requires using G can always be expressed in such a manner that the input of G itself, the argument that goes into G, can be always just dimensionless. So for example, these dimensionless inputs will often be the products of powers of dimensioned quantities with units, but the dimensions, or in other words, the units will cancel out to give a dimensionless number. And so the Buckingham Pi theorem says it's always possible to do this within this space of quantities. So for example, so here I had half of the power of 10 minutes, which is not obvious what that would mean. But here for radioactive decay, I have half to the power of, and then I have a time, but that's been normalized by the half-life. And so this ratio is a dimensionless number. And so I can then exponentiate the dimensionless number. So that's an example of Buckingham Pi theorem, sort of, or the spirit of it. Okay, so far I've been talking about numbers that are, or quantities that are the combination of a dimensionless number and a multiplicative unit. Now, I started earlier with a conversation between person A and person B. I'm now going to have another conversation between person A and person B that's going to be analogous, but with an interesting difference. Person A, I hear you've been trying to broaden your vocal range. What's the lowest pitch you're currently able to sing? Person B, it's about minus 1.5 octaves. Person A, sorry, what pitch was that? Minus 1.5 octaves. Still room for improvement. It's nowhere near as low as person C, who can sing at minus 2 octaves. Person A. So person C can sing half an octave lower than you can. But I still don't know how low you or person C can sing. So to quantify pitch, you can't do it using just a number. But you also can't do it using just a number of octaves, like minus 1.5 octaves. That's not a pitch, right? An octave is actually just another example of a dimensionless unit, like a radian. So an octave we can just think of as just the number 1. So to quantify pitch, you can do it using a number of octaves added to a reference pitch. So for example, middle C minus 1.5 octaves. That's an example of a pitch. And that would be the same as if I use a different reference pitch, A4 minus 2¼ octaves, or C2 plus half of an octave. And so pitches are not dimensionless numbers. You can't quantify them just as just a number. But differences in pitch are dimensionless numbers. We measure them in octaves, for example, but octaves are just, as I said, dimensionless number. So pitches are not dimensionless, but differences in pitch are dimensionless. And compare this with how earlier we talked about time durations. Time durations are not dimensionless numbers, but ratios of time durations are dimensionless numbers. So in the first example, it's the ratios that are dimensionless. In this example, it's the differences that are dimensionless. And so when we talked about time durations, they had a multiplicative unit, but pitches have, we can think of them as an additive unit. So these reference pitches, we can think of these as an additive unit to which we add the dimensionless number. So it's not really the way we're used to thinking about units, but it makes perfect sense, and we use it effectively for quantifying pitches. Now, does the Buckingham Pi theorem imply that we should not be allowed to take logarithms of quantities like 50 hertz? Well, let's think about this. There are many physical quantities that are naturally quantified via a logarithmic representation of a dimensioned quantity. For example, pH, pitch, as we've discussed, and loudness. And in this paper from 1991, the notion was suggested of taking logarithms of dimensioned quantities, like 50 hertz, where the logarithm of a multiplicative unit becomes an additive unit. Let me give you an example. Acidity or basicity of solutions is measured by pH, and pH is conventionally defined as minus log base 10 of the hydrogen ion concentration as measured in moles per decimeter cubed. Right? So this numerator has the same dimension as the denominator, meaning that when we take the ratio, we're just putting in a dimensionless number into the logarithm. So for example, for water, the pH is approximately 7. But here's the thing. The value of this denominator, moles per decimeter cubed, is completely arbitrary. As far as I'm aware, it has no physical significance in connection with acidity or basicity. So this is a kind of redundant overcomplication. And similarly, I also think that this base 10 is similarly arbitrary, although I guess perhaps it's connected with why. I think the P stands for percent. So I don't know if, but anyway, from a physical point of view, this base 10 is arbitrary. We use 10 because we count in 10 because we have 10 fingers, but that's got nothing to do with acidity or basicity of solutions. So instead, let's more simply define the pH as minus the natural log of the hydrogen ion concentration without the denominators. And so then inverting that, the hydrogen ion concentration would be e to the power of minus pH. So in this case, for example, the pH of water that was previously 7, pH of water would now be 16 plus the natural log of decimeters cubed per mole. But as I said, there's nothing special about decimeters cubed per mole. So we can also express this in other ways. We can change the units to whatever we want here, as long as it's the right dimension, and then the numbers just change in front accordingly. A bit like we're used to for normal units, you change, where you multiplicative units, you change the units and then you divide as appropriate, except here we now just need to sort of add and subtract as appropriate when the input of the log is multiplied or divided as appropriate. Another example, I've talked about pitch, but we can think of pitch as being the log base 2 of frequency. So for perception of sound, 2 is the more natural base than anything else. And then similarly, frequency is just 2 to the power of pitch. So for example, if we consider this equation about frequencies, so 3520 hertz is 440 hertz times 8, we can now take the logarithm base 2 of both sides of this equation. So the logarithm of 3520 hertz becomes the pitch A7, logarithm of 440 hertz becomes the pitch A4, and logarithm of 8 is just 3. Or I can say 3 octaves, but the octave is a dimensionless number. So let me now address some sort of objections that might be raised to this idea of logarithms of quantities with units in the way I've described. First objection is some people might assume, or some people have thought in the past, that it's mathematically inconsistent. But it's not, it's perfectly consistent. The vector space structure of the conventional positive valued quantities that I presented earlier translates directly onto the space of their logarithms because of the vector space structure. So for example, the log of this diffusion coefficient, you can break it up into its fundamental units using addition and subtraction. Next objection, an expression like log base 10 of a gram has no meaning. Right, because there's no physically meaningful object that I can raise 10 to the power of to recover a gram. The answer? Well, it's just a mathematical tool, just like the conventional operations of multiplying dimensioned quantities or raising them to non-integer powers. That was just a mathematical tool that everyone is happy with, and this is just another mathematical tool. So sort of philosophically, an expression like this derives its meaning from the equations that define it. And then next possible objection, it's never necessary to take logarithms of dimensioned quantities. By the Buckingham Pi theorem, one can always express the input of the logarithm as a dimensionless ratio. The answer, well, some things that arguably might not be necessary are still extremely useful. For example, being able to multiply two lengths to define an area. It's probably not necessary, but it's very useful. Being able to take the square root of a quantity, like in the Brownian motion diffusion coefficients, simplifying an extremely complicated mathematical expression is not necessary, but it's useful. Negative numbers are not necessary. Complex numbers are not necessary. Calculus with complex numbers are not necessary, but they're all extremely useful. So then last objection is someone, because most people have never seen something like this before, they'll naturally think, well, surely it must never be actually useful. Well, we've already seen how it simplifies and removes unnatural terms from the definition of pH. We've also seen how it makes for a natural definition of pitch as the log base 2 of frequency. And this last point is what I want to explore in the remaining time in this talk. So a fair amount of what I'm about to say is sort of overlaps with what I said in the sort of introduction to Moda I gave yesterday, but it's definitely worth reiterating. So the sound coming into our ears includes oscillations across a multiplicatively broad range of frequencies. In other words, a broad range on a logarithmic scale. Our ear distinguishes different sounds by time frequency analysis, which means at each time it discerns the frequency content of the air pressure time series entering it locally around that time. Now, the sensation of this frequency content that the ear discerns represents these frequencies logarithmically, i.e. as pitches. We hear differences in pitch, not differences in frequency. And this representation as logarithmic sensation of frequencies is appropriate for the multiplicatively broad range of frequencies present in time series. Or in other words, the linearly broad range of log frequencies. It's not just the facility of hearing for which these considerations I've described are important. Signals involving oscillations across a multiplicatively broad range of frequencies occur throughout sciences. And so this kind of logarithmic approach becomes appropriate very broadly. So I've talked about time frequency analysis, which is what the ear does. So let me say a bit more about time frequency analysis and also frequency analysis without the time in front. So the basic approach to discerning and quantifying oscillatory components in a time series is estimation of what's called the power spectral density using the Fourier transform of the signal. So power spectral density assigns a non-negative value to every frequency f. So the idea is when you then have a peak around some frequency f0, that may suggest an oscillatory component of that frequency f0. Now, power spectral density is not a time frequency analysis because it does not provide a time evolving description of the frequency content. Instead, it treats the whole time duration of the signal in one go. Now, this is going to be the key point. Sometimes one is interested in the total amount of oscillatory content within some frequency range, some frequency band. For example, I think in neuroscience, some of the different types of neural wave are defined in terms of different frequency bands, I think. And so using power spectral density, a way to measure the total amount of oscillatory content within a frequency band is the power of that frequency band, which in this, using PSD, it would be simply defined as the integral of the power spectral density with respect to the input frequency from the lower end of the frequency band to the upper end of the frequency band. So it's just very simple integral over the frequency band of power spectral density with respect to frequency. And in particular, sometimes we wish to compare this power across different frequency bands. How does the power in one frequency band compare with the power in another frequency band? Okay, so that was power spectral density, but often we need to be able to see the changing characteristics of an oscillatory process. For example, it might have its frequency being modulated. And also sometimes you have temporally intermittent existence of oscillations. So oscillations exist and then don't exist and so on. You want to be able to see these things. And so just doing the power spectral density of your signal won't capture these things. So as in the ear, we need a time-evolving description of the time-localized frequency content. And that's what time frequency analysis is. Now, one common approach to time frequency analysis is the windowed Fourier transform. So I mentioned the Fourier transform is used often for sort of power spectral density. Here, for the windowed Fourier transform, we perform the Fourier transform of the signal, but not the whole signal. Instead, it's the signal confined to a sliding time window. And so if I have a signal x, then this G subscript X, that's my notation for the windowed Fourier transform, of any given input frequency f at a time t, that's equal to the value assigned to this frequency f by the Fourier transform of the signal within the time window localized around time t. So we do the Fourier transform of the signal to get the sort of value associated to frequency f, but just confined to this window around the time t, and then this t slides along. And so using this, we can get a notion of a time evolving power spectral density, which is just the squared modulus of this quantity. And then, just as before, we want to take the power of a frequency band, but now we can follow that in time. So the time localized power of a frequency band, once again, it's the integral over the frequency range of the power spectral density. But now it depends on time. So the power of this frequency band depends on time. So it's a time localized power. Now, one thing I do need to say, I've been talking about the time window, but actually these time windows do not have a sharp start time and end time. Instead, they can fade in and out, for example, according to a Gaussian shape of sort of fading in and out. And so then the parameter for a sort of Gaussian shaped time window is just the width of the window, except by width of the window, when it's actually infinite width. So what I would actually mean here is the standard deviation of the Gaussian shape. That would be the width of the window, which I'm denoting sigma. Now, we have the Heisenberg-Gabor uncertainty principle, which is very important in time frequency analysis, which is that to have a more clearly defined description of the frequency content around time t requires a broader time window around that time to be able to investigate the oscillations better, but that then gives a less clearly defined description of the temporal changes of frequency content. So you have this trade-off between frequency resolution and time resolution or time localization. And incidentally, in the windowed Fourier transform, which I've been describing, these Gaussian shaped windows are the optimal shape of windows for the sort of joint time frequency resolution. So that's the theorem. Now, there are some important limitations of the windowed Fourier transform for studying systems with a multiplicatively broad range of timescales involved. We have this window, this sliding window, but we use the same, and then we do the Fourier transform within this window. But this fixed window width is likely to either have too poor time localization for studying higher frequency content, or too poor frequency resolution for studying the lower frequency content. Because, as I said, there's this trade-off between time localization and frequency resolution. Let me elaborate particularly on this latter point. So the results of the windowed Fourier transform are totally meaningless for frequencies below some minimum value, right? Because for your given window width, if you have really slow oscillations, then your window width is not wide enough to capture anything about those oscillations. So the results are totally meaningless for very low frequencies. And another related issue. So when you do a frequency analysis, oscillatory components they're represented as a positive frequency, but they're often also represented as a negative frequency as well. Now we're interested, we look at the positive frequencies, but they exist in the negative frequency axis as well. And because we have this imperfect frequency resolution due to this Heisenberg principle, some of this imprecision of frequency resolution can spill over from the negative frequency axis into the positive frequency axis that we're studying, and vice versa. And so you have this, for low, when you're looking at low frequencies, you can have this interference from negative frequencies. And so a solution to this problem of the fixed window width that doesn't adapt to the different frequencies under investigation is provided by using the wavelet transform, or continuous wavelet transform, which I'm denoting W, in place of the windowed Fourier transform, which I'm denoting G. I realize I don't have a timepiece. I should check. Okay. So very roughly speaking, the way the wavelet transform works is for each frequency f under consideration, you do the calculation of the windowed Fourier transform, but the window width is rescaled is in inverse proportion with f itself. Now, technically, in the sort of standard definitions of the wavelet transform, the first argument of this function is not actually frequency, but is rather time scale. But the time scale of an oscillation can simply be regarded as proportional to its time period, which is 1 over the frequency. And so I'm just using frequency as the input rather than time scale. They're just inversely related. And so the key point is this window width rescaling for investigating the different frequencies means that the time windows envelop a consistent number of time periods of oscillation across the different possible frequencies that you can be looking at. Now, if we were to perform the calculation that I've described naively, then for the higher frequencies, you have narrower windows, and then the calculation will then, as a result, end up giving you artificially smaller magnitude values just because you've got a narrower window. And so it's normal then in the wavelet transform to include an amplification factor that's proportional to the frequency to the power of some number p to compensate for the narrowing of the window, just so that the calculation gives appropriate results. And so I've used this symbol W for the wavelet transform. I'm going to use this superscript P for the amplification factor. Sorry, for the exponent P in this amplification factor. So in particular, choosing P equals to 1, so that will mean that the amplification factor exactly matches the narrowing of the window. So that's, for example, what's used in Moda and in MATLAB. This will mean that equal amplitude oscillations in your input signal, or equal power oscillations, which is equivalent, at different frequencies will appear with the same sort of intensity, the same magnitude in my wavelet transform. So P equals 1 feels like a very natural choice. Now, I should say, technically, the wavelet transform doesn't use windows, but rather wavelets. But you can think intuitively, sort of in terms of sort of Fourier transform inside a window, but technically it's wavelets. And so just as there are different possible choices of window shape for the windowed Fourier transform, so likewise there are different possible choices of wavelet shape for the wavelet transform. Now, recall I said earlier that if I'm using the windowed Fourier transform, if I want to do the power of a frequency band at some time t, I just integrate the power spectral density as defined by the windowed Fourier transform from frequency f1 to f2. Now, if instead I'm using the wavelet transform, I want to define the power of a frequency band, then the naive thing to do would just be to replace the windowed Fourier transform with the wavelet transform. Can anyone see a potential problem that might arise with this? Especially if I'm interested in comparing the power across different frequency bands. Okay. The value of P would significantly affect the results for comparing power across different frequency bands. And so I need to, if I'm going to use this, I need to care about what value of P is the correct one, if any. If there even any value of P that will give a sort of an appropriate way of comparing the power of frequency bands. So it turns out, in order to obtain results that are compatible with the already existing notions of power of oscillations, then you need to take P equal to 1/2. Incidentally, another thing, the actual choice of wavelet used also needs to be what's called admissible. Otherwise, you can't do wavelet power spectra. So, how am I doing? What time did I start? Was it about 10 past? Did I start, or quarter past?
Either another 5 minutes. Then questions.
Okay.
Yeah.
Okay. Thank
Okay,
you.
relax. We have a long lunch break. So
Okay. Yeah. Okay. Thank you. So problem using p equal to a half, and that's what we use for the wavelet power spectrum, doesn't match the choice of p equals 1 that we would want to use to make equal power oscillations at different frequencies look the same in the wavelet transform. So in other words, there's a kind of seems to be a kind of inevitable bias when using the wavelet transform, as has been discussed apparently in the atmosphere-ocean community. The second problem is that this choice of p equals to a half is specifically connected with power spectra. There are also so-called higher order spectra, and for these, the p equals to a half would be completely irrelevant. Okay. Now, in terms of the choice of the wavelet shape itself, one choice is what I'm going to call the uncorrected Morley wavelet. And so the idea is this corresponds to doing the Gaussian windowed Fourier transform, but just with the rescaling of the window width as in the wavelet transform. Right? So this is done because Gaussians are nice, as I've explained. However, the problem with this is that this fails a so-called admissibility criterion. It's not an admissible wavelet. So technically, the implications of this is that it can't be used to construct a wavelet power spectrum, and also it's very difficult to reconstruct a signal from its wavelet transform when using a non-admissible wavelet. And so, as a result of this, one often encounters a corrected Morley wavelet, where a very small magnitude extra Gaussian term is added in the formula. But there's another problem here. So this is now the third problem I'm mentioning. This extra term that's added to make the Morley wavelet admissible has no physical meaning. It's just an artificial fudge to make the theory work. And then there's another interesting problem. The Morley wavelet, in other words, this Gaussian one, with or without its correction, fails to be what's called analytic. So what does that mean? Do you remember I talked about this interference from negative frequencies in the windowed Fourier transform? Well, for a non-analytic wavelet, this interference from negative frequencies also occurs. And not only that, because of this window rescaling in the wavelet transform, this negative frequency interference doesn't just happen when you're looking at low frequencies, but it's carried up through all the frequencies that you might be interested in looking at. And so from that point of view, that sort of makes the wavelet transform worse than the windowed Fourier transform. Now, one can use other fudges, additional fudges to the Morley wavelet to cut off negative frequency interference, but this loses the desired Gaussianness. So I've mentioned 4 problems, and I'm now going to present the simultaneous solution to all 4 of these problems. So the frequency resolution of time frequency analysis is linear for the windowed Fourier transform and logarithmic for the wavelet transform. So what do I mean by that? So here in the left column, the input signal is a 1 Hertz oscillation. In the right column, it's a 5 Hertz oscillation. Now, in the top row is the windowed Fourier transform, and you see that these look the same except just shifted up. In the bottom row is the wavelet transform, and again, these look the same except just shifted up. However, for the windowed Fourier transform, this frequency axis is linear, and that's what makes them look the same. Here, for the wavelet transform, this frequency axis is logarithmic, and that's what makes these look the same. So these look the same on a logarithmic scale. So that's what I mean when I say the wavelet transform has logarithmic frequency resolution. And so, in the same way as in the windowed Fourier transform, we treat frequency as our independent variable. So I was meant to say independent variable. So in the wavelet transform, just as in our sensation of sound, it's natural to treat log frequency rather than frequency as the independent variable. And in addition to helping with the maths, as we'll see, it also makes conceptual sense to think in this way of log frequencies as the independent variable when thinking about sort of systems with a multiplicatively broad range of frequencies, which is what motivated the wavelet transform in the first place. So now I will have to quickly skim over how this ends up solving simultaneously all four problems. Rather than using Gaussian wavelets, it's more natural to work with kind of log Gaussian wavelets. I won't go into the technicalities, but these wavelets are admissible for solving problem 3, and they're analytic, solving problem 4. And the reasons for both of these are very much connected with this logarithmic frequency approach. And incidentally, when you consider time frequency resolution properties with the logarithmic frequency resolution, then it turns out that log normal wavelets seem to have better resolution properties than the Morley wavelets. Now, recall that for the continuous wavelet transform, I said that the power of a frequency band is the integral of the power spectral density using p equal to 1/2. And this was the source of my other two problems. Now, equivalently, I can replace the 1/2 with 1. So the point is we wanted 1 in our, we preferred having p equal to 1, but that introduces a factor of 1/f in the integral. Right, because this is the f to the power of 1/2 amplification factor. So replacing the 1/2 with 1 introduces an f here. Now, this may look familiar from the start of the talk. So to recall our first slide, so I said that these two integrals are different perspectives on the same physical object. It's just the third one that was the more complicated one. So the power of a frequency band, if you now think of it as the power of a log frequency band, this division by f that I had, I can now turn that into an exponential. So what we're doing is we're taking, so the power of a log frequency band is now the integral from the lower log frequency to the upper log frequency of the power spectral density squared, like we want. It's just that it's power spectral density with respect to log frequency rather than with respect to frequency. And this enables us to keep our p equal to 1. So we've resolved this discrepancy between p equal 1 and p equal 1/2 that we had earlier. And actually, no, I should mention first. So what's going on in terms of dimensions? So these increments d zeta, you can think of as dimensionless, even though the zeta values themselves are not dimensionless, but are log frequencies, or in other words, pitches. Incidentally, if you're working with a logarithmic discretization of the frequency axis, which is normal for the wavelet transform, for example, that's what's done in Moda, then this expression is the most efficient form in which to compute this integral. So that's another nice advantage of this logarithmic frequency approach with wavelets. And incidentally, so remember my problem 2 was that the p equal to 1/2 was specific to power spectra, but it would be irrelevant for higher order spectra. Well, it's been shown that for, well, at least for third order spectra, when you use this logarithmic frequency approach, then the choice of p equals 1 is consistent. It applies both for second order spectra and the higher order spectra. And so this solves problem 2, at least going up to third order spectra, although defining fourth and higher order spectra for wavelets hasn't been done yet. So we've now solved all 4 problems. So why was this magic solution not adopted from the outset? Well, I suspect that part of the answer is the following. The expression for wavelet power using this logarithmic frequency approach, if I want to do it in a way that is compatible with or consistent with the conventional approach to dimensional analysis, where you have where you multiply units and you can raise them to powers, but you can't take a logarithm of one. If you want to express this logarithmic approach in a manner consistent with classical dimensional analysis, then it needs to be of the form 3 in my first slide, right? That's this one with the redundant c, this extra complicated one that was the most unsimplified. In other words, it would need to look like this, where we have this extra number phi, which is the redundant arbitrary frequency value that's used to make the argument of the logarithms dimensionless. A bit like how moles per decimeter cubed were used to create dimensions of log in the definition of pH. And the point is, no one would consider this expression to be as simple as just as one without the log frequencies, let alone the even simpler one where we use p equal to 1/2. So this looks a lot simpler than this. And so because people are used to thinking in multiplicative dimensions and never additive units and logarithms of normal quantities, then people would be less naturally lean towards taking this logarithmic frequency approach because of this ugly representation. Okay, well, so just to conclude, so additive units have just the sound and mathematical foundation as multiplicative units. We already use these in quantifying pitch. One can soundly define logarithms of quantities with multiplicative units, where the result is just a quantity with additive units. And as an example, we've seen that log frequencies are the natural independent variable to use for defining time-localized frequency spectra, so provided by the wavelet transform. Okay, and here are references. Thank you very much.